Hi class, so now we're on 12.3. In this lesson, we're going to cover three types of reactions that involve acids and bases. We have acid and base neutralization, reactions of acids with metals, and the formation of acids with non-metal oxides. So we introduced acid-base neutralization reactions, which was in chapter 6. Recall that these reactions as an acid and a hydroxide base combine to produce water and an ionic compound that we refer to as a salt. For example, hydrofluoric acid reacts with sodium hydroxide as shown here. The proton from the acid combines with the hydroxide from the base, forming water. The remaining ions end up together as sodium fluoride. Similarly, perchloric acid reacts with potassium hydroxide. Again, the proton from the acid reacts with the hydroxide from the excuse me, can't understand my own writing, from the hydroxide base to form water. The remaining ions combine to produce a salt. What drives a neutralization reaction to take place? To understand this, it is helpful to rewrite the reaction as a complete ionic equation. Notice the potassium and the chlorate ions are unchanged in this reaction. They're spectator ions. The net ionic reaction for neutralization is a combination of a proton and hydroxide to form water. The formation of water drives the neutralization reactions. So if it's an acid-base neutralization reaction, then the net ionic equation is going to be water. Let's look at an example. Write a balanced equation to show the reaction of aqueous nitric acid with aqueous calcium hydroxide. We begin with the two reactants, nitric acid and calcium hydroxide. In this reaction, the proton from the acid and the hydroxide from the base combine to produce water. The remaining ions, which are calcium and nitrate, combine to produce an ionic compound, calcium nitrate. A simple way to balance neutralization reactions is to balance the number of protons and hydroxide ions that combine. Because calcium contains two hydroxide ions, two hydrogen ions are required to react with it. This produces two waters. This produces two water molecules, and our equation is now balanced. So what they're saying is focus on this, and that will give you this, and then it will balance out the rest. Most metals react with acid to produce metal cations and hydrogen gas. For example, iron metal reacts with hydrobromic acid to produce iron 2 bromide and hydrogen gas. We can write this as either a molecular equation or as a net ionic equation. So you can see here is the molecular, and you should understand how to do both. This is a molecular equation, and here is net ionic. What actually plays a part in the actual reaction itself, and not everything is. So if you break this into an ionic equation, you'll see what plays a part. This produces hydrogen gas. So obviously there's going to be something here that's going to change, which is going to be the iron, but the chloride is going to stay the same, and it's not going to change. We're going to get into more of this as this section goes on. So if what I'm saying right now doesn't make sense, we're going to start breaking down reactions in a different way. So you're going to understand what this means later on, because the metal is reacting, and that's where, so if you see, this is two protons. It took the two electrons from iron, which is why it's now a metal, and once it did, it made it a diatomic gas. So that's why this is playing a part, where what you'll notice is that the chlorine, if we break this up, nothing happens. It stays in the same form on both sides. Okay, so similarly, this is tin, SN is tin, reacts with nitric acid to produce aluminum nitrate and hydrogen gas. Again, we can show this reaction as a molecular equation or a net ionic equation. So there is a common theme here, is that metals tend to produce, when they're in a combination with an acid, tend to produce hydrogen gas as a product. So that's what you're seeing here. Not all, but this is what we're also going to learn as we go on. Similarly, precious metals, silver, gold, and platinum, do not react with acid. For example, this image shows gold wire in hydrochloric acid. The gold does not react the way most metals do. In fact, the reason these metals are precious is that they are rare, beautiful, and durable. They are not easily destroyed or chemically changed the way more common metals are. So objects made from precious metals, like this Incan figurine, can stay in beautiful condition for centuries. As their name implies, non-metal oxides are compounds or ions that contain a non-metal covalently bonded to one or more oxygen atoms. Many non-metal oxides react with water to form acids. For example, carbon dioxide reversibly reacts with water to form carbonic acid. This is not a stable product, but I'm not going to get into that right now. But if it's put together, yes, carbonic acid. In carbonated beverages, the beer and soda, the dissolved CO2 forms carbonic acid through this reaction. As well, we see later lessons, this reaction occurs with carbon dioxide dissolved in the bloodstream, a process that helps regulate acid and base balance in the blood. I don't think we're going to get to that chapter. Okay, sulfur oxides and nitrogen oxides also react with water to form acidic compounds. For example, sulfur trioxide reacts to form sulfuric acid, while reacts to form nitric acid. Did I read that right? For example, sulfur trioxide reacts to form sulfuric acid. Feels like something's wrong. While dinitrogen pentaoxide reacts to form nitric acid. There we go. These reactions are important because sulfur and nitrogen are common in fossil fuels such as coal and oil. Burning these italics, dirty fuels is what they're called, can produce sulfur oxides and nitrogen oxides. These oxides combine with moisture in the air, leading to the effect known as acid rain. In heavily industrial areas, acid rain accelerates erosion and is harmful to plant and animal life. To minimize the effects of acid rain, most first world nations have developed strategies to remove nitrogen oxides and sulfur oxides from fossil fuel emissions. For example, coal burning plants use scrubbers to trap the sulfur oxides and nitrogen oxide gases, preventing their emission into the atmosphere. While these technologies are not perfect, they produce a dramatic effect in air quality over the century. That's why we have catalytic converters in our car, because they change some of the emissions into something else, but you need very precious metals in order to do that. And that's why, if you notice, people are stealing catalytic converters because of what's inside that helps. It's a catalyst, which means it helps these reactions occur. And what's produced out of the car is not as harmful as if that didn't have that catalytic converter. So reactions involving acids and bases. So an acid base produces water and a salt. That's a neutralization reaction. Reactions of acids with metals, an acid plus a metal tends to produce a salt and a hydrogen gas. These tend to be single replacement reactions because the metal tends to be in solid form by itself. Formation of acids, and you will actually have a list on the printout that I gave you, which we'll be covering, I think, in the next lesson. Formation of acids from non-metal oxides. Non-metal oxide plus water produces an acid. Complete and balance the following reactions. So I'm just going to show you these to you because you should by now be starting to understand what you need to do. So here is an acid and a base, water and a salt. You can see the water is being produced and the salt. Complete and balance the following reactions. So in this case, single replacement reaction, single replacement reaction, single replacement reaction, single replacement reaction. All metals, all produce hydrogen gas. Most metals react with acid to produce hydrogen gas. Most. Next lesson, we're going to cover which ones apply. Predict the products from this reaction. So you see we have a metal by itself, we have an acid, the product is a gas, and the salt. Which compound reacts with water to produce an acid? And that's going to be nitrogen trihydride.